2:40. Let me just set up the warm-up question, then I'll make a few announcements and we'll cycle back and see how you did. So last time we got through the geocentric model, the ancient Greek models for the universe, the models of Aristotle and Ptolemy, which make use of deference and epicycles. And so this is a two-part question. In the first part, I'm asking you how many deferents are in the standard geocentric model. And don't worry about the sphere of fixed stars, and just everything else. How many deferents? Pick a number between 0 and 9. And then how many epicycles in the standard model? Pick a number between 0 and 9, and then combine those two numbers together into a 2-digit number and submit that to the interface. So while you're thinking through that, I have a few other quick announcements. First of all, homework 2, I've postponed it 1 week. So it's not going to be due this Friday, it'll be due next Friday. And part of that is we don't have class on Monday because of Labor Day. And I think I'll be able to get through everything for lesson 2 early on in Wednesday's lecture. So I'm trying to catch up, and delaying the homework a whole nother week makes me feel sad, but I think I am getting closer to being caught up, and maybe we'll see that by the time we tackle homework 3. And then the other announcement I have is today we're going to continue through the heliocentric model, talking about evidence in favor for it and disproofs of the geocentric model. And then there's a video that I want you to watch, 12 minutes on other more modern proofs, disproofs of the geocentric model. It involves some demos and things I really can't do in my room. It is listed here. So if we go to the Skynet YouTube site, down here to the bottom where we're putting our COVID lectures, under the lesson 2 playlist, you can see there's the Stonehenge lecture. Here's the last lecture. I'll add today's lecture after it, and then watch this 12-minute video to complete the discussion of disproofs of the geocentric model before the next lecture on Wednesday. Okay, that's it for announcements. Let's see how we're doing with this. I'll give you another 10, 20 seconds with me being silent so you can think. Nothing. Thanks, everyone. Well, let's see what we have here in terms of values. And we'll take a look at the histogram. And yeah, a plurality got it right. Some of you chose 1, 1. I'm not really sure why. But other than that response, yeah, 7, 5 is the correct answer. Let's take a look at that real quick. Let's put up the answer on the dot cam. So here's our standard geocentric model. And other than the fixed stars, which I told you to ignore, it involves the 5 naked eye planets and the sun and the moon. So that's how you have your 7 deferents. Each planet and the sun and the moon have a deferent, but only the 5 planets have epicycles. The epicycles were introduced to explain the retrograde motion, the non-uniform motion. The sun and the moon, they move around Earth in the geocentric model uniformly, so they do not have epicycles. So 7 and 5. Okay. Let's see. Last time we had begun the heliocentric model. I'll put some notes back here. The heliocentric model of the universe. And we talked about Aristarchus, who was the first to propose it. And again, here are his dates, so a long time ago, BC. And he basically presented the modern day heliocentric model, and I'll write out the details of what that is again in a second. But the thing that everyone got stuck on is the rotation of the Earth. As we talked about last time, we're on a rotating planet, but why don't we feel that rotation? And that's the question Aristarchus got. Aristarchus claimed that we were on a rotating planet. No one feels that rotation. It's not until you get all the way to Newton, you can actually calculate the magnitude of that force. It's in the westward direction, and it's small compared to the force of gravity. And that's why we don't really notice it. You really notice it on large scales, like it creates weather, drives global weather, creates large-scale weather systems like hurricanes and cyclones and things of that nature. Anyway, Aristarchus got caught up on this force, the Coriolis effect, and the heliocentric model kind of was dropped all the way until Copernicus. So this is 1473 to 1543 AD. So a long, long time the geocentric model ruled, and for some time after this as well. Copernicus is going to reintroduce it. Let me just spell it out again. The sun is at the center of all things, and Earth spins, rotates on its axis. Earth is just one of the planets, not special, or not any more special than that. And Earth and the planets, they orbit the sun. And finally, the moon orbits the Earth. In the geocentric model, everything goes around the Earth. Earth is the most important thing in the universe, hence everything must go around us. But in the heliocentric model, the planets go around the sun, but you can have moons go around planets. Okay. So that's the basic model. That's what we've been taught since we were little children, but you still have to pass the same 3 tests that we talked about last time. Let's write them down again. You need to explain retrograde motion. You need to explain brightness variations. Planets are always brighter when in retrograde. And you have to explain Mercury and Venus always being within some angle of the sun. They're always near the sun in the sky. And it turns out that in the heliocentric model, although none of these may be apparent immediately, I'm going to demonstrate these are all freebies. You get these for free in the heliocentric model. In the geocentric model, you had to require them. You had to require that Mercury's and Venus's epicycles remained on a line between the Earth and the sun. You got retrograde motion because you introduced epicycles. And so you made special things and required special things to satisfy these constraints. In the heliocentric model, you get it all for free. So let's start with retrograde motion. So here we have Copernicus and retrograde motion in the heliocentric model. So there are no epicycles. The planets aren't going to be going through loops like in the geocentric model. Instead, what causes it is we're observing the planets from Earth, and Earth is no longer stationary. Earth is moving around the sun. So we're observing the other planets from a moving platform, and that creates the appearance of retrograde motion. So here's a figure, and let me explain it. We have the sun, we have 2 planets, Earth and Mars, and I don't know, perhaps the best way to think about this is think of 2 runners going around a track. The sun is at the center, Earth is on the inside track, so has a shorter distance to go. Also, let's say Earth is the faster runner. And then we have, in this case, it's the planet Mars on the outside track, so longer to travel, also a slower runner. And the question is, where does Mars appear in the sky from Earth's point of view? Now, we got the sky back here, those are the stars. Imagine that as the audience, the stadium full of people. So let's say you're Earth, and here we are at time 1, and you take a look at Mars. Maybe Mars is up here further ahead, and so you'll see Mars superimposed on this part of the stadium. Then at time 2, you've both advanced in your orbit. You see Mars superimposed on this part of the stadium, or this part of the sky. And that's the prograde west to east motion. Time 3, still prograde motion, time 4, still prograde, time 5, still prograde. But then we're going to pass Mars. We're on the inside track, we're the faster runner, so we will go ahead of Mars. Then if we want to see Mars, we have to turn our head and look back behind us. So at time 6, we see Mars over here. That's retrograde motion. They were over in this part of the stadium, blocking that part of the stadium, and now they appear to block this part. At time 7, they've gone even farther back. But then we both start rounding the curve. At time 8, Mars appears to be moving prograde again. Time 9, prograde. 10, 11, so forth, prograde. And so we'll only go into retrograde. We'll only see retrograde when we're passing a planet. But it happens for free. Now, I know looking at this diagram and listening to those words, you may not fully get it. So normally when we're in a classroom, I have some volunteers come down and we just act this out. We run around 2 tracks and mark the position on the wall. So I'm just going to play a video of that from, I don't know, probably about a decade ago. Let's see here. And I'm going to talk on the video. I'm just going to be quiet and let old me talk.
Put up here.
Young me.
2 volunteers. Oh, okay. 1, 2. Let's see. Let's make some running room here. And I'll be Earth. First one here gets to be Mars. Okay. And you're going to Mars where Mars appears to be to me on the wall. So let's kind of set this up. Now you're going to be on the outer track. Let's start you here. I'm going to be on the inner track, and we'll run in fits and spurts. So I actually can't keep up with you because I'm a lot older than you. Okay. Right now, I see you in the sky over there. So wherever I'm pointed, go stick a sticky note on the wall. Okay. Now go ahead and run part way. And okay, stop there. Okay. Go ahead and stick on the wall over there somewhere. Okay, run a little bit more. Okay, stop. Okay, a little bit further, and I just caught up with you. Well, I tried to. 1 second. There we go. Okay, now I'm gonna. Okay, you stop. Okay, say we hit retrograde. We went backwards. Okay, you keep running. Now I'm going around the track. Now we're going forward again. Sorry about that, but you also we'll do one more step. So if we were being clever about it, we would have taken a few more snapshots during the retrograde to spell it out. But at least you saw it go into retrograde a little bit there before we went to prograde again. Thanks, guys.
Okay. I don't know if the quality came across, but did you follow? Okay. And let me show you one more thing. I'll put the dock cam back up. One more demo to depict how you get retrograde motion for free. Let me turn this around and put it up here. So this is something I found in the attic of Phillips Hall, which is a frightening place. I don't know why I was up there, but I recognized what it was as soon as I saw it. It's a retrograde motion machine. I'll come over here and use it. So we have the sun. The racquetball here is Earth. The little hard red ball is Mars. And by turning the crank, we're going to orbit counterclockwise. And right now we're in retrograde. Earth is just passing Mars. So the arrow shows the direction from Earth to Mars. Retrograde, but now it's prograde, 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 prograde. We're on opposite sides. Prograde, prograde, prograde. And now when I pass, watch the arrow goes back. Retrograde, retrograde, retrograde. And then we return to prograde, 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 and retrograde, 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 and then back to prograde. So every time we pass Mars, no matter where it happens to be in the orbit, that's when we get the retrograde cycle. Okay. Okay, that makes sense, how we get retrograde for free in the heliocentric model? Okay, good. Also, brightness variations. We get that for free too, because it's always brightest when in retrograde, and just like in the geocentric model, here in the heliocentric model, that's when we're closest. So it makes sense. We're closest to Mars when we pass it, so it'll be brightest when we pass it, and that's when we have retrograde motion. So the retrograde motion, the brightness variations, those are two freebies. Now, why is Venus and Mercury always close to the sun? So here we have a schematic, heliocentric model, sun at the center. Here we have Earth going around the sun, that's the black circle. The red circle is any outer planet, Mars, Jupiter, Saturn, Uranus, Neptune, etc. And then we have the inner planets, Mercury and Venus in blue. Let's start with the outer planets. They can be anywhere in our sky. They can be exactly opposite the sun. So from our point of view, if the sun's over here, opposite would be over here. And so if the planet's at this part of its orbit, we call that opposition, meaning opposite from the sun. Or it can be all the way over here in the same part of the sky as the sun. We call that conjunction. So any planet that's farther out than us can be anywhere in the sky. But if it's closer in, then, I'm not going to test you on these terms, conjunction and opposition, but I will define them anyway. So let's say we have an interior planet. It can also be in the same part of the sky as the sun in two different ways. It can be between us and the sun. We call that inferior conjunction. And then over here, it's still the same part of the sky as the sun, just on the far side of the sun. We call that superior conjunction. But the farthest that these interior worlds can get from the sun would be this position and this position. Here's an angle, and if you were at any greater angle, you would be off the orbit. And you have to be on your orbit. So interior worlds are automatically confined to lie within a particular angle of the sun. And you could pretend this is Venus's orbit. Mercury would be closer in, so it would be an even tighter angle. But again, it's automatic. Just by being closer to the sun, it's automatically going to be always within a certain angle of the sun, Mercury and Venus. So you get the three criteria for free. Let's put the doc cam back up. So the great beauty of Copernicus's model is its simplicity. Remember last time we talked about Occam's razor? If you have multiple models, the simpler one is usually the correct one. So this has simplicity. So it's very attractive as a physical theory. But how accurate is it? At least this initial model. This is kind of the basic model of Copernicus, and then you're going to see he has a more advanced one. The basic model is beautiful in its simplicity, but it's not very good at predicting where the planets are in the sky. Ptolemy's model is better than Copernicus's basic model. And it just means Copernicus is missing something. There's something still missing, because we know it is a heliocentric worldview. Earth's not at the center of all things. We are orbiting the sun. It's just Copernicus hasn't figured it all out. Now, Copernicus built this model, and he didn't want a model that's worse than the geocentric model, so he tweaked it. What Copernicus did is he added epicycles, little ones, not big ones like the geocentric model uses. These are just little epicycles, but he needed to add them. He also shifted the deferent. Didn't need to shift the epicycles, but anyway, he added epicycles, he added shifts, and so the model is no longer simple. Once you add these things, it is accurate. It's actually a little bit more accurate than Ptolemy's, just a little bit. So it's comparable, maybe a little bit better, but it's no longer simple. So once he made it accurate, he undermined the best thing about the model. So again, the point is something is still missing. It's not that the heliocentric model is wrong, it's just something's missing from our story. And we actually won't get the answer until we get to Kepler. Okay, let me see where we are. Oh yeah, so Copernicus did all this work, put it out there, but no one took it seriously for a number of reasons. And let's write these reasons down. The first reason is he wrote it in Latin, which is the language of the academic, but back then. But very few people could read Latin. So this was only for a very, very small sliver of the population, people who already have an academic interest. The second and probably bigger problem was that it was published posthumously, published at death. On purpose. He had worked this out long before he died, but he didn't have it published until after he died. Anyone want to speculate why?
Because of the church.
Like hunted.
That's right. The church, the Catholic Church in this case, they had accepted the Ptolemaic model. You know, it's been around for so long, 13 centuries or so, and that it had been adopted by world religions and by the Catholic Church. And so this is now equivalent to Word of God. And Copernicus knew he was then questioning the Word of God, questioning church teachings, church dogma. And back then, the church had all the power, and it's not something you readily did. So he waited until he died, and then the publisher got antsy. And so there's, let's see, the publisher's disclaimer. The publisher put a note right on the front. I think I have it here. It's in Latin, so I can't read it. But the note basically says that don't take this very seriously. It's just an academic mathematical exercise. So that works against it as well. And then, of course, what you mentioned, it's a gross violation of church teaching of the time. So given all these things, no one took it seriously. In fact, the church wasn't worried about it enough to ban it for another 76 years. And that's when they were dealing with Galileo, who we'll get to next. But it wasn't a threat to the church by any means. Yet, Copernicus has now reintroduced the idea that hasn't been looked at since the time of Aristarchus. Okay, let's throw Galileo in here. Galileo Galilei, 1564 to 1642 AD. Again, you don't have to remember these dates, just kind of the relative orders of things. Yeah, know it to a century or so. Now, Galileo, he is an experimentalist. He's the first modern day scientist. There were no scientists before Galileo, not in the modern sense. There were academics, but they had a very different view of nature and their role in explaining it. They believed that anything that was worth knowing was figured out ages ago by the Greeks and other, ancient philosophers. And their job as academics was to pass this information on without forgetting some of it, without losing it, but certainly not change it. Pass it on as pristine and accurately as you can. Don't change it. Certainly don't challenge it. And that's what the modern day scientist does. The modern day scientist questions everything. You put an idea out there, then it's the job of every other scientist to question it and see if it's possibly wrong. So, Galileo is the first modern day scientist. He is performing experiments to try to find new knowledge and to question pre-existing old knowledge. So he wasn't liked by the academics, and as you can imagine, he certainly wasn't liked by the church. He didn't have very many friends. And he also famously had a terrible ego, huge ego. He loved giving talks and ridiculing all of his opponents, especially if they're sitting before him. So he's not really good at making friends and influencing people, and this will have some bearing on the rest of his life. Anyway, he did introduce the scientific method. Now, that's a phrase that you've heard ever since grade school, the scientific method. You've probably heard it in every science class, and probably no one ever really explained to you what it is. So I put together this flow chart that I think captures the crux of what the scientific method is. So it begins with the hypothesis. I'm going to walk us through this so you have a good understanding. It begins with the hypothesis, an idea. And there are two types of hypotheses, those that make testable predictions and those that don't. And most testable hypotheses actually fall into this second category. They're just ideas that you can't really confirm or deny. Whole philosophies, religions, they fall into this category. And that's okay. That's not to put them down or discredit them. Science can't deal with everything. We can only deal with ideas that make testable hypotheses. Lots of things in our everyday existence don't fall under that category. And so we have all these other structures to help us get through our day-to-day life and our existence. But the point is, those do not fall under the realm of science. Ideas that cannot be tested, that's not science. And it's not a path to new knowledge. It's just something you take it or you leave it. You accept it on faith or you don't. Now, science deals with these testable predictions. If you have an idea, a hypothesis that makes a testable prediction, then you design the experiment to test it. Or in the case of astronomy, we can't design experiments with cosmic bodies, so we have to observe a lot of the universe looking for this experiment actually happening out there in space. And then you can have two results. If the result is inconsistent with the prediction, then the idea is wrong. And this is the most powerful idea behind the scientific method. If you have a hypothesis, it makes a prediction, you go and test it, the prediction's wrong, the idea is wrong. You only have to be wrong once, and the idea is flat out wrong. Now, humans are fallible, so sometimes we can make a mistake while we're doing a test. So you're going to want to repeat the test multiple times. It's best if it's tested by different people in different ways to rule against human error. But eventually you do all this, and if an idea is, if it fails the test, the idea is wrong. And that is useful. If a hypothesis is disproved, that is new knowledge. You know that this idea is no longer worth your time and consideration, and you should spend your time doing something else, considering other ideas. So you come back here, make a new hypothesis. Now, if your hypothesis passed the test, this is the other part that people don't really appreciate. It does not prove the idea. Science doesn't prove anything to be correct. If it passes your test, then that idea gains some credibility. It may be right. It's not guaranteed to be right. It may be right. And then you cycle back and see if that idea makes any other testable predictions. And you keep going through this circle here. And the more times you go through it, the more credibility the idea gets. In particular, if you can make predictions that are very specific or strange or obscure, things that wouldn't happen just by chance, and it passes those tests, you gain a lot of credibility. So science is a path to truth, but it's a messy path. It doesn't tell you which way to go. It tells you which way not to go. If you have an idea, you think of it as a random walk. You try this idea, no, that didn't work. Oh, walk over here. No, that didn't work. That didn't work. Okay, that worked, so I'm going to keep heading in that direction. Even if an idea passes lots of tests, you can think of that as a model of absolute truth. The scientific method is based on the assumption that absolute truth exists. And this is a path to get closer and closer to it. We don't know if we ever get all the way there. We don't know if some of the things we know are absolute truths or just better and better approximations thereof. A good example is gravity. Newton, as we'll learn in a few lessons, came up with the theory of gravity. It passed every test for centuries, but then it started failing a few more difficult, trickier tests. And Einstein came along and came up with his theory of relativity, general relativity, which is a replacement for Newton's theory of gravity. And to date, it's passed every test that's ever been thrown at it. Is it absolute truth? Maybe, maybe not. We have another theory in physics, quantum mechanics. It's the theory of the very small. In fact, these are the two pillars of modern physics. Einstein's theory of general relativity, a theory of gravity, a theory of the universe on large scales, and quantum mechanics, which was put together by many people, the theory of atoms and nuclei and the universe on very small scales. Turns out they're built on contradictory postulates. One assumes that you know where objects are and where they're going with absolute precision. The other, the better you know one, the worse you know the other. So even Einstein's theory of gravity, which has passed every test, probably is not absolute truth because it stands in contradiction to quantum mechanics. It means there's going to be At some point in the future, we'll have a new Einstein, and they'll come up with a new iteration. And maybe that will be closer to absolute truth. Maybe it will be absolute truth, but we'll never know. Anyway, I went on and on there, but hopefully there are some insights as to how science is actually done. Okay, let's get back to Galileo. So back to Galileo here. And what Galileo did, I'll put the dot cam up. He was an experimentalist, and experimentalists need instruments, and his instrument was the telescope. He was the first to take a telescope and point it at the sky. He did not invent the telescope. That's a common misconception. It was invented shortly before this, probably for military application. If you can see your enemies coming from farther out, you have more time to prepare. Very practical military instrument. But he took one of these and pointed it up at the sky, at the four brightest objects in the sky: the moon, the sun, Jupiter, and Venus. And with each one of them, he made a revolutionary discovery. So 4 revolutionary discoveries, and this all happened in 1609. Each one of these would have been a Nobel Prize back in the day if they had them. Let's tackle the moon first. Now, the first 2 don't really address the geocentric, heliocentric debate, but they do stand in opposition to things that the church had adopted and were teaching, along with the geocentric model. So with the moon, I just wrote moon on the dot cam. The church believed the moon and the sun were, quote, perfect objects. By perfect, they meant perfectly smooth. And in the case of the moon, it's splotchy. There are dark regions and light regions. But so it wasn't perfect in that sense, but they believed it was perfectly smooth. With the sun, they thought it was perfectly uniform, no splotches, no spots, and also smooth. And this probably goes all the way back to Aristotle and Plato, those aesthetics, that circles are really important. You know, they're built into Ptolemy's model that had been adopted by the church. So it makes sense for them to also want to believe that these objects are perfect spheres and perfect circles. But if you take even a low-powered telescope or binoculars and point at the moon, not during full moon, you can't see it during full moon, but at any other phase, the division between day and night, the sun in this case is on the right-hand side of the picture, and it's casting long shadows to the left, and this makes it possible to see that the moon is not perfectly smooth. It has craters and mountains and bumps and ridges. It's not a perfect object by the church's definition. And then he pointed at the sun and saw spots. Now, if I were to look at the sun through a telescope, I'm sure I'd see spots too. I'm not exactly sure how he did this, but he made very careful drawings, and those have since been confirmed in the modern day. He detected sunspots, the first to do so. But these are blemishes on the surface of this supposedly perfect object. So both of these stood in contradiction to church doctrine, although they don't really address geocentric versus heliocentric. We get into that with the next one, Jupiter. He pointed the telescope at Jupiter and noticed these 4 points of light in a line about Jupiter. These are his actual drawings, his initial drawings of Jupiter through a telescope, January 7th, 8th, 10th, 11th, 12th, 13th, and 15th, 1609. And they're moving in this line, going around the planet. For the first time in the history of history, he's discovered new worlds in the cosmos, and they're not orbiting the Earth. And in the geocentric model, everything orbits the Earth. These 4 worlds, which we now call the Galilean satellites, the 4 large moons of Jupiter, they're orbiting Jupiter. So this was a big problem for the geocentric model, but not a big deal for the heliocentric model, because moons can go around planets in that model. Earth's moon goes around us. So it was a problem for the geocentric model, but it's not really a great test of the heliocentric model. The best test is the phases of Venus. This is the 4th one, and this is the one that people forget. See, I'm just writing these on the dot cam, which I'll put back up. The phases of Venus. In the geocentric and heliocentric model, you get very different predictions for the phases of Venus. Now, without a telescope, you can't see the phases. The naked eye can't see them. So they never were a problem for the geocentric model in the past, but now we have a telescope. So what predictions do the two models make? Here's the geocentric model, Earth at the center. Venus travels on an epicycle, and the center of the epicycle is on a line between the Earth and the sun, always. So these are all the different positions Venus can be in. Here it's a new Venus because it's between us and the sun. And as we move over here, it becomes a crescent. But then we come back between the Earth and the sun. So it goes from new to crescent to new to crescent to new. You never achieve a quarter Venus or a gibbous or a full Venus in the geocentric model. It's always got to be a crescent or less. In the heliocentric model, sun's at the center. Here's the orbit of Venus, the orbit of Earth. And Venus can be between the sun and us, in which case it's new. And coming over here, it's a crescent. But if you keep going, it works its way behind the sun. So you do get a quarter Venus and a gibbous Venus and a full Venus. Although we can't see the full Venus because the sun is in the way, but we see it approaching full Venus, and then you go through the phases coming back the other way. So these are very specific and differing predictions between the two models, and here are observations. The phases of Venus, and indeed we do get a gibbous and a full Venus, which again, very specifically rules out the geocentric model. And as I was saying, it's even better if you can make very precise predictions. And notice how the phase correlates with the size. There'll be a new Venus when it's large and a full Venus when it's small, and you can make very specific predictions. When it's this phase, it should be this big. And that's exactly what we see. Here's new or almost new. It's very large because it's close to us. When it's full, it's very far away, and the sizes match the phases exactly. So that gives the heliocentric model a lot of credibility. It made a very specific prediction, and that's borne out by the observations. So again, here's our flow chart. Two hypotheses, geocentric and heliocentric. The geocentric flowed down this path. It was disproved by observation, so it's wrong. The heliocentric flows down this path. It met the observations, so it gains a lot of credibility. Okay, so Galileo wrote this up. Let me advance in my notes. Okay, and bring up the doc cam. So Galileo wrote this up. I'll just slide this over and put the notes on the same page in a book that's called The Dialogue. Dialogue Concerning the Two Chief World Systems is the full title, but we normally just call it The Dialogue. No, I'm sorry. I've jumped ahead of my notes. That's incorrect. This is The Starry Messenger. We'll get to the dialogue in a second. The Starry Messenger made his discoveries in 1609, had them published by 1610, which is really good turnaround, even in the modern era, to turn around a scientific result that quickly. So kudos to him. And this basically presented his results. Of course, the Starry Messenger is referring to himself. Again, this big ego. He's bringing truth onto the masses. He's the messenger, the Starry Messenger. Described these amazing results, went around, gave these public talks, challenging religion, challenging science of the day, the academics of the day, would publicly ridicule the Aristotelians and their geocentric model, with them right there in the audience. And he figured, I can get away with this because as soon as they look through a telescope, they'll have to admit I'm right. Thing is, the telescope was new, they weren't very good, and there were no other modern day scientists to use them. He was the only one. And he began to realize there's a problem, that no one could verify his results because they weren't scientists, they weren't experimentalists. He started having telescopes made and shipped to nobles and kings and dukes. And there's story after story of them getting these tubes, holding them up to the sky, half the time backwards, half the time looking at clouds, even if it was dark, half the time during the day, when the sky's bright. But even when it was dark, So they had difficulty pointing at the various objects, holding them steady, taking careful measurements, being patient, all the things a modern day scientist has to do. They had no skill for it, and so they'd just throw them in the garbage. And so even though it was as simple as looking through a telescope, there just wasn't anyone around who could do it. And very quickly, the church in particular got pissed off with him and banned his book. It actually went for about 6 years. It was banned in, I'm writing on the dot cam, 1616. Banned in 1616. And he wasn't allowed to talk about this at that point. And that stayed that way for a long time until eventually, let me check the time, I have 10 minutes, okay. Eventually, there was a new pope, Pope Urban VIII, here he is, and he didn't know Galileo, but he knew the Medici family, and they were Galileo's sponsors. They paid his salary. And so a connection was made, and Galileo was granted an audience with the new pope, met with them, said, I'm sorry, I got carried away back then. I won't do it again. Give me one more chance, and I'll present both sides, and I'll present it in, to use a modern phrase, a fair and balanced manner. And Galileo went on and presented it in the modern sense of that phrase. It wasn't particularly fair and balanced. But the Pope said, okay, you can do this, but in the end, you have to come to the conclusion that the geocentric model is correct. Because who are we, mere mortals, to know the mind of God? Who are we to question the word of God? I'm paraphrasing, but this is essentially what Urban VIII told him. And Galileo, having no other option, said, fine, I'll do it. And the Pope really wasn't too concerned, figured Galileo would go off and write some boring academic treatise with lots of equations in Latin that no one could read, and he wasn't worried about it. Because in the end, he was going to conclude the geocentric model is correct, and people would just walk away with that no matter what he wrote and forget about it. That's not what Galileo did. So he wrote his next book on this subject in 1632. This is the dialogue. So I'll write that again here. Dialogue concerning the two chief world systems, 1632. He waited 16 years for this opportunity since it was banned. And did he write a boring academic treatise? No. He wrote a narrative with fictional characters, entertaining fictional characters. He made it a story. So let me flip my pages here. Here's the cover in the first page. There's a moderator. I forget the name of the moderator, but the moderator is essentially Galileo. He's moderating this debate between two characters, Salviati. So let me put up the dot cam here again. So arguing on behalf of the heliocentric model, we have Salviati. And on the geocentric model, the name of the fictional character that he chose was Simplicio. So already you can see he's not playing it down the middle. So Simplicio is simpleton. A simpleton will argue on behalf of the geocentric model. And he did present both sides, but the heliocentric model comes across better. And it should, because there's actual facts and data to back it up. It's difficult to present something that's true at the same, on the same equal level as something that's obviously not true. But he gave it a go. And then in the end, he decided to balance it out by giving Simplicio the last word, giving the geocentric model the last word. And the word that he gave Simplicio was the geocentric model has to be correct because who are we, mere mortals, to know the mind of God? Who are we to question the word of God? So what he did is he took the words of Pope Urban VIII, put them in the mouth of a fictional character whose name was Simpleton, and published this book. Even worse, he published the book not in Latin, which very few people could read, but it was published in Italian. There we go, Italian. And literacy back then isn't what it is nowadays, but a lot more people could read Italian than could read Latin. So then the shit hit the fan, right? And the church is not going to be happy with this. He was given his one chance, and he just went for it. So let's see, this was in 1632, and in the very same year, he was called before the Inquisition. Now, he didn't go in 1632. He was a little nervous about this encounter, which is natural. Here's a famous painting of him standing there, all kind of standing his ground and defending his position, but that's not at all what happened. By 1633, he did go. His friends convinced him, you better actually show up for this or it's going to end very badly for you. And he basically acquiesced right away to everything they wanted. He was ordered to denounce his writings, which he did. And then he was ordered to house arrest for the rest of his life. So, could have ended worse. He got to go home. He just couldn't leave his home. People would bring him food. There's an interesting correspondence he had with his daughter that's recently been published in a book called Galileo's Daughter. That's a good read. She was a nun at the time. And he slowly went blind and then died. And that's the end of the sad story of Galileo. Now, the church is an institution of forgiveness. And eventually they did forgive Galileo for his crimes. Anyone know when this happened?
It was pretty recently, was it?
1992, yeah. Now I'm playing on words a little bit. They not only forgave him, but they admitted that they were wrong and that we don't live in a geocentric universe. It is the heliocentric worldview. And I don't mean to pick on the church and the Catholic Church in particular here. I'm picking on them historically. Historically, they were wrong. But I think they learned a lot from this encounter with Galileo and the fallout in the years afterwards, as it was shown that the geocentric model is wrong and the heliocentric model is right. The Catholic Church is actually very pro-science compared to other world religions, the modern day Catholic Church. For example, the Big Bang Theory, and it's really only a theory. Back in the 60s, when it was named, it was a theory, but there's so much evidence for it now. It's a theory like the theory of gravity is a theory. If I were to drop this pen, we know what's going to happen. If you take Astro 102, we spend a lot of time going through all the mountains of evidence. Anyway, the Catholic Church accepts the Big Bang Theory. They also accept evolution. Now, of course, from their point of view, God created the universe, God created us, but the Big Bang and evolution is the mechanism of this creation. Anyway, compared to some other religions, they're very pro-science, so I don't mean to give them too hard of a time. Now, I think that is it for today. I just want to remind you, once again, I put that extra video here on aberration of starlight and stellar parallax. These are tests that occurred in the mid-1700s and the mid-1800s that finally sealed the deal, killed off the geocentric model, and verified with great confidence the heliocentric worldview. So definitely read that or watch that. It's only about 12 minutes before next time. Parallax in particular is a key concept that we'll keep coming back to. Okay, we ended 2 minutes early today. I'll leave it there. See you next time.
Thank you.
My pleasure.
Thanks.
Thank you.
Thank you.
Thank you.
Thank you.
Sorry, what is that name? The heliocentric model character's name?
There's Galileo, and before Galileo, there's Copernicus.
Or sorry, the character. So not Simplicio.
Salviati.
Salviati. Awesome. Thank you.
Yep.
Appreciate it.
Sure.
Do we know that Galileo was actually dryly looking through a telescope at the sun, or did he have like something that would maybe not make him go blind?
I would certainly want to use a filter of some type, but even if you just, most things that you might think would be an adequate filter are still not adequate. So I don't know if he tried to block some of the light to make it less painful, or if he just looked at it. My understanding is he just looked at it. there are also techniques that you can use where you project it out of the back of the telescope onto a piece of paper or something. But my understanding is he looked at it, but it didn't make him go blind. And it doesn't always. You can look at the sun and not go blind, but you can also look at the sun and go blind. So it's just something you have to be careful about.
Well, it was something I was thinking of because, like, I don't even think I could muster up the courage to look through my telescope at the sun. That would be horrible. Like, I can barely look at the full moon through my telescope and, like, feel like I'm going to lose my eyesight.
Yeah, but your telescope's probably a lot more powerful than his. His was comparable to weak binoculars and not very good ones.
Was he using, was he back then, was it more like a reflector or a refractor?
It was a refractor. It was a long tube. The optical elements on both sides, they had to be handmade. They're not very good. I had a colleague who built some replicas. We just used PVC for the tube, and we purchased the optics matching Galileo's prescription. So these are like professionally made optics, but boy, they're hard to use. They're hard to focus. You can focus only the center or the edges, not both. I've never seen, I'm lucky if I can get them to focus on a nearby building. And they were a little bit better than Galileo. So kudos to him for actually making these observations.
All right, that's cool. Thank you.
Sure. Anything else? Going.